Well, essentially, what I want to understand is how does the ocean mix? If you put a tracer in, it's going to spread horizontally, which is something that eddies do, along surfaces of constant density. All right? But it also can get mixed across density surfaces, and the two things are very different because the stirring by eddies is along isopycnals, and you need three-dimensional turbulence to actually put a tracer across a density surface. And so this turbulence, though, it happens on really small scales, and so you have specialized instrumentation to do this. If you are trying to make a prediction of, say, what the concentration is of oil, or it's the tracer, but you could use oil for an example, you want to know both how do the eddies carry it along, but also how much does the turbulence tend to mix the concentration and decrease it. And so the process of prediction typically happens with very large numerical models that are very intensively, that are very numerically intensive. And you can't simulate everything in those models. And in particular, you can't simulate the turbulence. You can simulate some of the things that are forcing the turbulence if you resolve the scales that you think are important for those. And so what we're thinking is important is that the deep Gulf, about 1,000 meters, has a lot of very complicated topography. So there's a lot of salt domes on there, and the typical scales between these mountains are 20 kilometers. And so it's very complicated. And what we think is going on is that flow over these mountains on the bottom of the ocean leads to things like downslope windstorms if you were on the surface of the ocean. So you go hiking and say you're in a saddle between mountains, there tends to be, just because the volume gets, or the area gets narrower, you're forcing flow through a gap, and you can have intense winds. But oftentimes what you would find is that the air goes up over the saddle, and then on the downslope side, you get very intense winds. And along with that, you have a lot of shear, very large velocity gradients that tend to be associated with a lot of turbulence. There's an end product, and then there is an intellectual product. The end product for the rest of the community probably is a statement that, well, we think the small scale topography, say on kilometer scale, is what's really important for determining the amount of mixing. But that actually is a pretty intensive calculation numerically. And what we hope to say is, well, if you have a computer and you only resolve 5 kilometers in your numerical model, that you're missing this much. And so you really need to go down to a kilometer. And if you get down to that scale, well, the physics that I'm seeing in terms of mixing may want much smaller scales to actually generate the turbulence that's going to mix. But if you tell me what's going on in 1 kilometer, then I can write a lot of math, a lot of complicated math that tells you how much mixing. And that's really the basis of the effort.